the Data Structures with Python ACE Technical Interview Series. And this session is going to be about graphs. So here are our proud Rishika, who is our track lead, and Jasmine, who is our evangelist. So this is our mission to inspire women to excel in technology careers. Our vision is our target, and this is our code of conduct. And we have a lot of members from all around the world, and this is our movement. And here are upcoming events. So we have another data structure session on July 9th about maps and hash tables. And stay connected. Please join us on social media. And I will get started. So my name is Nayeon. I'm a sophomore studying computer science and new media art. And I'm a general volunteer at Women Who Code Python track. So today's agenda. So this session is about graphs. So first we'll learn about the definition of graphs, and then we'll visit the applications of graphs, where graphs are used, and then the concepts of graphs, and then implementation of graphs. And in the implementation, we'll look at adjacency list and adjacency matrix. And then we'll also look at traversals in a graph, which are breadth first search and depth first search. And then after that, we'll do a Q&A. And then in the last part, we'll do live coding. So definition of a graph. So this is the definition of a graph. So graphs are not charts they're not in computer science. Graphs are not charts we use in our everyday life. Graphs are used to represent the relationships between data items. A graph consists of nodes or vertices and edges. Here, I would like to let you know that I'm going to use the terms nodes and vertices interchangeably. So here on the image, the circles are nodes or vertices, and the lines that connect the nodes are edges. Applications of a graph. There are a lot of applications of graphs in networking, transportation, gameplay, and even in some AI apps. So in networking, it is used in the internet, it is like how the internet is connected can be represented by a graph. And regarding transportation, the system of roads or the airline flights from city to city can also be represented by graphs. And concepts of a graph. There are two components of a graph. So first is V, which refers to the set of vertices, and E refers to the set of edges. We use uppercase letters here. And vertex is the singular form of vertices. A vertex can have a key, which is the name, and it can also have payload, which is for additional information. And an edge is also called arc, but we usually use the term edge. And an edge connects two vertices. So if two vertices are connected, then that means they're related. And an edge can be one-way or two-way. So in this image, we have circles that represent vertices and lines that are edges. And we can classify graphs by some standard. So first, we can use direction. We can look at whether the edges are directed or not. In graph A, it is undirected graph, because so undirected means that we don't, so For example, if we start from this node, we can go to this node and then we can come back. So there's no like a set direction. We can go to like two-way. So therefore it is an undirected graph. But in contrast, in graph B, notice that we have like arrowheads and edges. So this means that the edges are directed, and therefore the graph is a directed graph. So the edges are one-way edges, and a directed graph is also called digraph. Another way to classify graphs, another way to divide graphs is to see whether or not they have weight. Weight is the cost to go from one vertex from another. For example, so let's think about weight as the distance between two cities in a graph of roads. So for example, we have a graph. Let's think that we have a graph of roads that connect the pairs of cities. And in this graph, the weight can be the distance between two cities. And then on the left, we have unweighted graph. This means that we don't have any weight attached to each node, each edge. But on the right, we have weighted graph. So if you look at here, we have numbers that are next to each edge. So this edge has the weight of 12, this has the weight of -2, and so on. So there are additional concepts that are worth to visit. So first we'll look at cardinality. A cardinality in a graph is the number of something. So the cardinality of vertices will be the number of vertices we have in a graph. And similarly, the cardinality of edges will be the number of edges. And cardinality is represented by two bars. So we have V, which is a set of vertices. And if we enclose it with two bars, it means the cardinality of vertices or the number of vertices. And in E, the E enclosed with two bars means the cardinality or the number of edges. In this particular graph, we have, so what is the cardinality of vertices? We can just count the number of vertices here. 1, 2, 3, 4, 5, 6. So the cardinality of vertices is 6. On the other hand, the cardinality of edges, for that we can just count the number of edges. 1, 2, 3, 4, 5, 6, 7. So the number or the cardinality of edges is 7. And another concept that we'll visit is degree. A degree of a vertex is the number of edges that are connected, that are directly connected to a vertex. So here, for example, if we think about the degree of vertex 4, it is 3 because the number of edges attached to the vertex 4 is 3. 1, 2, 3. And if you look at the vertex 6, we only have one edge attached to it, so the degree of vertex 6 is 1. And then, sorry, I forgot like a slide about like degree, not before the degree, before introducing degree, but I'll just move on. And then the next concept we'll visit is adjacent vertices. So what we mean by adjacent vertices is that we refer to a pair of vertices that have an edge between them, that have a direct edge between them. So for example, in this graph, 6 and 4 have a direct edge between them, so they are adjacent. And 4 and 3 are also adjacent, and so are 1 and 2. However, 5 and 3 are not adjacent because although we can go to 5 from 3 or vice versa, 5 and 3 do not share a direct edge. Therefore, they're not adjacent. And then another concept we'll talk about is path. A path in a graph is the sequence of vertices that are connected by edges. So here are some examples of paths, and this is not an exhaustive list. So if we start at 6, we can go to 4 and 5 and 2 and 1. And if we start at 3, we can go to 4 and 6. And then if we start at 3 again and then go to 2, we can go 3, 2, 5, and 4. This is a definition of a path. A path is the sequence of vertices that are connected by edges. And the last concept we will visit is a cycle. A cycle in a graph is a path that starts and ends at the same vertex. And a cyclic graph means a graph without any cycles. And a graph that is acyclic and directed is a directed acyclic graph, which is abbreviated as DAG. So here in this example, if we think about some examples of cycle, we can start at 4 and we can go 4, 3, 2, 5, and 4. And the important thing here is that a cycle must end at the same vertex. Therefore, we need to write the last vertex, which is going to be the same as the first vertex. We cannot just end at 5 because that's just gonna be a path. So if we start at 4, we need to end at 4. And another example of a cycle will be 1, 5, 2, and 1. And another example will be if we start at 3, we can do 3, 2, 5, 4, and 3. An implementation of a graph. We have 2 ways, which the first is to use an adjacency list. Adjacency list, so in this implementation, we're first writing every node in the first column. So we have 1, 2, 3, and 5. And then here, in each row, we write out what neighbors each node has. So 1 has neighbors 2 and 5, so we write 1 to 5. And then 2 has neighbors that are 1, 5, 4, and 3. And here we are writing the neighbors in a non-decreasing order. So it is like increasing in this case. And 3 has neighbors 2 and 4. 4 has neighbors 2, 3, 5. And 5 has neighbors 1, 2, and 4. We are only writing the direct neighbors. And another implementation of a graph is by using an adjacency matrix. An adjacency matrix is a 2-dimensional matrix, and we write out all the nodes in the first row and in the first column. The first row will be the starting node, and the first column will be the column. So I have a question on the Q&A, but I'll go over it in the Q&A part later. So here, if we have a direct edge between these 2 nodes, this pair of vertices, we're going to write 1. But if we do not have a direct edge, we're just going to write 0. So if we start at 1 and end at 1, we don't have an edge that goes from 1 and ends at 1. So we write 0. But on the other hand, if we start at 2 and we go to 1, we do have a direct edge, so we write 1. And similarly, we just fill out the matrix by judging whether we have a direct edge between vertices. So because we have two implementations to use, we can think, you might be wondering, so which implementation should we use? So actually the number of vertices doesn't really matter in determining which one we need to use, but the number of edges do, or does. It does matter. If a graph is sparse means that we have a lot of vertices, but they're not very connected densely. That means that the cardinality of edges is a lot smaller than the cardinality of vertices squared. And we use squared because in a 2D matrix, so in this graph we have 5 nodes, and in this matrix we do the number of cells we have, except for the labels, is 5 times 5, so 25. And if a graph is sparse, we use an adjacency list, and we'll think about why later. And if it is dense, the cardinality of edges is going to be close to the cardinality of vertices squared, so it doesn't really matter. If the graph is sparse, so what do you mean by sparse? It means most cells are empty. So if a graph is sparse, we don't have a lot of direct edges between pairs of nodes or vertices. And that means that if we draw adjacency matrix for a sparse graph, we will end up having a lot of empty cells, which is going to be a waste. So it'll be better to just use an adjacency list for a sparse graph. And in an adjacency matrix, one of the advantages of using it is that we can learn quickly whether an edge exists between two vertices. So for example, if I just want to learn if 5 and 1, without looking at the actual image of the graph, if I want to learn if 5 and 1 share a direct edge, I can just go to the matrix and then just see, oh, 5 and 1 does share an edge. So this is the advantage of using a matrix. And then we can look at traversals. So we have breadth first search and depth first search. We'll first look at the breadth first search. First, we will visit all the vertices at the first level. So in a breadth first search, we are visiting all the vertices in the first level. And then equivalently, we are going to visit the vertices that are one step away. So first, we'll be visiting all the vertices at the first level. And when we are complete visiting all the vertices at the first level, we'll move on to the next level. And then we'll visit the vertices that are one step away. And when we're done with that, when we're done with visiting all the vertices that are one step away, we'll move to another level. And then we're going to visit the vertices that are 2 steps away, and then 3 steps away, and then repeat until all the vertices in the graph have been visited. For example, this is an example of a breadth first search. This is a graph, and if we start at 4, the next level, the nodes at the next level are 3 and 5. And in this example, we are going to visit the smaller ones first. It's not like a strict rule, but we're just it's just our rule. So because 3 is smaller than 5, we will first visit 3. And then 5 is also at the same level as 3, so we'll visit 5. And after that, the nodes at the next level are 2 and 6. And because 2 is smaller, we'll visit 2 first. Then after that, we are going to visit 6 that are at the same level as 2. And after that, we'll visit the nodes at the last level. And because 1 is smaller than 7, we'll first visit 1 and then 7. And after that, since we have visited all the nodes, we are done. And then depth first search. It is different from breadth first search. It is another traversal, another way we traverse through a graph. So first, in a depth first search, we go as deep as possible until there's no adjacent vertex. And then we backtrack, where we go back when there's no adjacent vertex. We backtrack, or we go back and check for other vertices. And then we repeat the same thing until we visit all the vertices in a graph. So if we also start at 4, in this example again, we're going to visit the smaller ones first. So we have 3 and 5 in the next level. And because 3 is smaller, we'll go to 3. And then this is the depth first search. So instead of visiting 5, we are just going as deep as possible. So we are going to visit the next level, the node at the next level, which is 2. Then we visit the next node, which is 7. And because we don't have any more adjacent vertices, we're going to backtrack and start at 5 because 5 hasn't been visited, but it is at the lowest level from 4. So we visit 5, and then the next level we have 6, and for the next level we have 1. And once we have visited all the nodes, we are done. So Q&A time. So I'm not really sure if I need to read the chat or Q&A, but first Q&A. Are all the vertices unique? That's a really good question. Let's go back. So you mean all the vertices? Stephanie would like to answer this question live. Stephanie, do you want to answer that question?
I'm just marking it for you, so when you answer it live.
Oh, I see, I see. Yeah. So are all the vertices unique? So what do you mean by unique? Just you mean like, are all the vertices have different data items? Is that what you mean? Okay. Yeah. So are all the vertices unique? Not necessarily. So there can be for example, so in this particular example, I just I just gave the nodes different data items because I wanted to differentiate each one. But we can have like more than one item, one vertices that have the same value. So the conclusion is all the vertices can be unique, or they don't have to be. So not necessarily. In BFS, how come we get to know 4 is at the first level? Good question. So BFS, let's go back to BFS. So there's actually no hard and fast, there's no strict rule when it comes to deciding what do we want to become our to like when it comes to like selecting the first node, there's no strict rule. And I just wanted to start at 4, and that's why I marked 4 in the first place. And if you can, and if there's time later, please tell why you started 4. I just wanted to do this because in this particular example, it is like starting at 4 would make it really like easy for you to spot the difference between a depth first search and a breadth first search. Do you have any other questions? Yeah, you're welcome. Thank you so much for asking questions. I'm gonna wait for like 30 seconds or 1 minute to see if any of you have more questions. Please feel free to ask me any questions. You can even ask me questions about my background or what I'm doing at Women of Code. So far we have got 3 questions and the chat. Excellent. Yeah, excellent questions. Please feel free to drop any questions you have in the Q&A. Are you able to place the link in the chat? Oh, the live coding. I'm gonna do that. So I didn't like, I was not really like planning to make it like what I was planning to do for the live coding was that I was just gonna just code with you, but I'm gonna make anyone with the link be able to edit. And this is the collab. I hope you are seeing this without any problems. I think I can get started. So intro to the data structures with Python graphs session. This agenda. So this live coding is going to be really simple because for me, I actually didn't really know what I needed to do for live coding. There wasn't like very much to do for live coding. It was like graphs were more about like theoretical parts when I was learning about graphs. So today's agenda, so we'll just look at how we can implement adjacency list and adjacency matrix and traversals. This is what we are going to focus on in this live coding part. We have breadth first search and depth first search. And implementations. So we have adjacency list. And for an adjacency list, we can just use a dictionary in Python. So in graph, so we have, let's say we have nodes A, B, C, D, E, F. Then the set we use, by using set, we can just we can just write out what the neighbors A has. And this is just an example. So from here, we know that A has neighbors B and C, B has neighbors ADE, and C has neighbors AF, and so on. And because, so set in a set, there's no particular ordering. And in an adjacency list, so even though on our slides, we ordered the neighbors in a non-decreasing order, there didn't necessarily have to be like a strict ordering. So we can just like write out the neighbors as like however we want it. So in an adjacency list, we can just use a dictionary of vertices and its edges. So it's just going to be a sufficient representation of a graph. And in an adjacency matrix, we can just use nested list in Python. So nested lists are like the list inside lists. And here we have vertices or nodes. And this is the really important part of this like coding, which is going to be the implementation of traversals. Chat. What does the graph corresponding to the nested matrix look like? Good question. Actually, let me pull up Paint. Can you see my Paint? Sorry, I'm loading the Paint. Can you see my Paint? Whoops. Okay, yeah, thank you. So here, so matrix is like a table. So we are just gonna write out, so I omitted other nodes, but if you write out what the matrix would look like, it'll look like this. 5, 15, 0. I think I should just type it out. 5, 15, 0, 7, 10, 0. And then after that, we write 15, 0, etc., etc., etc. And this goes on. So this goes from top to bottom and left to right. And because it is a matrix, we'll have like, it'll be better if we have like grids. This is a really bad matrix. But if you represent the matrix if we just represent the nested list as a matrix, it'll look like this. So we start from left to right and top to bottom. Thank you for asking the question. And then for traversals. So let's suppose we have this unweighted and directed graph. I mean the graph. I have no idea what the matrix means in terms of graph. Could you elaborate, please? So you don't really get why we use matrix to represent a graph? Oh, would you like me to go back to the slides? Are you talking about this particular graph or this particular example, or just matrix in general? Sorry, I'm waiting for the reply. So you literally have no idea what the graph would look like. You don't see the questions. Oh, the questions are in the chat. Sorry about it. So somebody is asking, somebody's saying they have no idea what the matrix means in terms of the graph. Oh, let me pull up the pane again. I think in this, I think I used a wrong example. I was just going to, so in this, I apologize. In the slides, I mentioned that we're only using either 0 or 1 to represent a matrix, but here I just write it out like all numbers. But thank you for pointing out it today. I think like as like following what I have introduced, it should be just 0, 1, 0, 1 or something like that. Looks like the adjacency where you use. No, it's not equivalent. It was just to so the point was the point of this part was just to mention that we could use matrix a nested list to represent a matrix. Something like this. I apologize for the mistake. Do you have any other questions before I move on? You can see questions from attendees. Looks like so actually so the person who's asking questions is currently typing the questions in the chat. So I would ask you to enter your questions in the Q&A session if it is possible. But I'll read out this question this time. So, oh, you're right. Yeah, so everybody, please set your chat to all panelists and attendees. I apologize, I didn't notice that. So the person who was sending the questions were only sending to the panelists. So that was the reason you were not able to see it. So I am going to just repeat the question the person has asked. It was that how would the first adjacency list look like a matrix? Yeah, that's a really good question. Actually, let me pull up the pane again. So first, before just writing it as an adjacency matrix, like converting an adjacency list to a matrix, we can think about what the graph looks like. Here we have an edge, we have a node A, and node A has neighbors B and C. And then we can connect them. And B has neighbors A, B, and E. The graph doesn't necessarily need to look like a tree, but I'm just drawing like it. And B has A, D, E, and C has A, N, F. And D has just B, D is just connected to B, and E has B, N, F. And F has neighbors C and E. So this is what the graph would look like from the adjacency list. And we can, so to form an adjacency matrix from here, we can we first list all the nodes here, A, B, C, D, E, F, and then also in the first column, we write all the nodes A, B, C, D, E, F, and then we can just check. Oops, it was like caught up, so I'm gonna open it again. And then here, we can just so the and then the content of the matrix, the things inside the matrix will be determined by whether or not each pair of nodes have a direct edge. So if you look at A, we do not have an edge that starts from A and ends at A. So we can write 0 here. And so remember that the first row is the starting point and the first column is the destination. So starting from B and from A, we do have an edge. We do have a direct edge. So we're gonna write 1. And from C to A, we do have an edge. So we're gonna write 1 again. And from B to A, we can go to A from D, but we do not have a direct edge. So we're gonna write 0. So it's like true or false. So we're just writing 0 if this particular pair, we're writing 0 if this particular pair does not have a direct edge, but we write 1 if they do have a direct edge. And starting from E to A, we do not have a direct edge again, so we're gonna write 0. And from F to A, we also do not have a direct edge, so we write 0. And we repeat the same thing until we fill out all the cells. We are almost out of time, but so I am going to just quickly go over this, and then if we have more time, we can just look at the questions in the Q&A session. So traversals. So we have this example. We have unweighted and directed graph here. So in a breadth first search, if we started A, the breadth first search will be A, B, C. So we just assume that if nodes are at the same level, we're visiting the one that comes earlier in an alphabetical order. So if you start at A, unweighted and directed acyclic graph. Yeah, you're right. Oh, you have other 40 minutes, I see. So there's also no cycle here. And if we start at A, we can do A, B, C, and D, E, F. So let's see how we can implement the breadth first search. So here we are just representing the example graph in an adjacency list, but I just used a list instead of a set to represent the neighbors. And here's the algorithm. So we're gonna pick any node and visit the adjacent unvisited vertex and mark it as visited, display it or print it, and insert it in a queue. And if there's no remaining adjacent vertices left, we remove the first vertex from the queue and repeat step 1 and 2 until the queue is empty or the desired node is found. So this is the algorithm for the breadth first search. We'll pick any node first, and then we need to keep track of visited vertices and the vertices in a queue. So I have initialized two lists, one for visited vertices and the other for vertices for the key vertices for breadth first search. So in a breadth first search, thank you, Stephanie. In a breadth first search, I'm just calling it here, but we can think of how we can implement it. So we can have 3 parameters: visited, graph, and vertex. So visited will be a visited list, a list of visited index, visited vertices. And graph will be the graph in the form of dictionary. So you're talking about this. And vertex will be the starting vertex. The vertex, the node where we start the breadth first search. So the algorithm, starting from the algorithm, this is the breadth first search. So we're first going to append the vertex. So when we start a breadth first search, we'll first visit the vertex. So we'll append the vertex to the visited list. And after that, we also want to append it to the queue. Hi, Karen. And what we want to do is that we want to repeat step 1 and 2 until the queue is empty or the desired node is found. So we can write, so here we can write an iteration, a loop, and the condition will be at repeat as long as we have at least 1 item in the queue. So we can just write while queue, and then after that, insert it in the queue, remove the, if there is no remaining adjacent vertices, we are going to remove the first vertex from the queue. And because queue is implemented as a list and it is a first in first out data structure, we are going to pop 1 item at the first index from the queue. So 0, and we store it here. And then pick any node, visit the adjacent visited vertex, mark it as visited, display it, and insert it in the queue. So because we have marked the vertex as visited, oh, we need to, sorry about it, let me think, I'm kind of confused. So we first append vertex and to visited list and queue, and as long as we have at least 1 item, we are going to do something, which is step 1 and 2. And if there are no remaining adjacent vertices left, remove the first vertex from the queue. So we can totally, yeah, thank you. While queue, so in Python, we don't even need to do queue is not non. We can just do while queue, and if queue is non, the while loop is not going to be executed. So remove the first vertex from the queue. If there is no remaining, so as long as we have any item in the queue, we're gonna pop the first vertex from the queue. So we can update the vertex, which is a starting vertex, but we are updating to the first vertex from the queue. And because again, queue is the first in first out data structure, we can pop the item at the first index. And after that, what you want to do is that we repeat until, oh, we want to display the vertex because we have visited and inserted the vertex in a queue. So we want to print. And after when we print it, what you want to do is to repeat step 1 and 2 until the queue is empty, or for name, we need to do the same thing for the neighbors. Continue to the neighbors. So we want to get the neighbors of a vertex in the graph. So we can do for neighbor in graph, or because we are using dictionary, we can just do vertex for each neighbor of the vertex in the graph. We are doing the same thing. So we are doing we need to check. So when we're done with the vertex and we want to go to the neighbors, what we first want to do is to check if the neighbor has been visited or not. Because if it has been visited, we don't want to visit it again. So if neighbor is not in visited, this is not, I think this is not invalid. This is invalid syntax. If visitor is not, oh, I don't do this. If neighbor is not visited, so visited is a list that keeps track of visited vertices in the graph. And if the neighbor has not been visited, we're doing the same thing. We will visit the neighbor, so we'll append the neighbor to the visited list. And then we also want to append, after we visit the neighbor, we also want to append it to the queue. What does the last parameter for this method represent? And if the vertex, is it the vertex you're looking for or the vertex you're starting with? Yeah, that's a really good question. It is the starting vertex. It is, and in this example, we're not looking for any particular node, and because this is a directed graph, we want to start at A, because if we start at B or C or any other node, we cannot visit. Oh, sorry about it. Let me take it back. It doesn't really matter where we start. We can just like backtrack if we don't have any, if we reach the level where we do not have any adjacent vertices. But because it is convenient to think about, to visualize the breadth first search starting at A, I'm passing A as the last parameter. And in the last parameter, the vertex is represent the starting index. So it is where we start breadth first search. And if we run the code, hopefully no error. A, B, C, D, E, F. Yeah, and let's check the answer. So if we start at A, so A is, we are passing the starting node, starting vertex. And if we start at A and we do a breadth first search, we can do A, B, C, D, E, and F. So it is A, B, C, D, E, F. This is how we can implement the breadth first search. Then Q&A. How do we know about the indices of vertices correctly too? So before moving to depth first search, I'll try to answer the Q&As. So how do we know about the indices of vertices correctly to the use binary itself? Sorry, let me try to understand this question. How do we know about the indices of vertices correctly to use binary itself? Are you talking about so I do not want to mispronounce your name, but whoever asked this question, how do we know about the indices of vertices correctly to use the binary itself, 0 or 1? It is not clear to me that this implementation will account for a situation where we do not choose the root of the graph. Yeah, So so first let me try to answer the question about the binary thing. So I guess you're talking about the matrix, right? Will it print out? Okay, yeah. So how do you know about the indices of vertices correctly to use the binary itself? So we can just like this is a vertices. Correctly to use binary. I'm not really sure if I understand your question correctly, but we can just check if we can just like get the neighbors of, like, for example, in an AJC matrix, we can get the neighbors of a particular node, for example, like A, and then we have neighbors B and C. And because there is a direct edge between A and B and B and C, A and B and A and C, we're just we can just make it, we can just do, if there's a direct edge, we're gonna insert 1 in the cell in the matrix, or if there's no direct edge, we're going to insert 0. I hope it answers your question for the connection in adjacency matrix. And what is the necessity of having set in the value edges for each vertex in adjacency list? What is the necessity of having? I'm not really sure if I understand your question correctly or not. Please forgive my level of comprehension. I'm not really good at like understanding complicated things at once. Necessity having set in the value edges for each vertex in the engine. Oh, it doesn't really matter because the way we write out the neighbors of a particular node doesn't matter. So in this example, we are using a list, but we could have just like omitted set, because we use set here just to emphasize that there's no particular ordering. We don't necessarily need to write out the neighbors in like a particular order. And do we keep adding always? Looking at the edges. Are you saying, do you keep adding always looking at? What do you mean by adding always looking at the edges? Could you elaborate? And sorry, now I'm reading the chat. Is it the vertex you're looking for or the vertex you're starting with? I think I have answered it. Talking about adjacency list. Oh, do you keep adding always looking at the edges? You mean we add a new node to the graph, always considering what edges it has? Is that what you mean? Yeah, adjacency list is not order, it's a dictionary. Why set? What you mean? Why we use a set for an adjacency list? Because you're talking about like this value, right? Like this value or these values. It was just to. Yeah, you're right. It is not critical, but it was just to emphasize that. Again, I just explained it, but it was just to emphasize that there doesn't necessarily need to be a particular ordering when we write out the neighbors of a particular node. And then, have I missed any questions? And why we don't tell it in? You got it. We're caught up with questions. Yeah. I see. Do you think I should just like move on? Let me first finish that first search and then come back. Thank you. Then the first search, we are using the same graph. And then the algorithm is that we'll first pick any node. And if the node picked is unvisited, we're gonna mark it as visited and recur on all its adjacent nodes. And then after that, we're gonna repeat until all the nodes are visited or the node to be searched is found. So here we're not considering whether we're searching for a node, we're just focusing on how we can implement the depth first search. And visited, we can just like initialize a set to keep track of visited vertices. And here, the parameter, we have 3 parameters. Again, this the visited set. Graph is the graph in the form of dictionary here, and vertex, starting vertex. So the algorithm would be, we'll first pick any node or vertex, and this will be the starting vertex that it will be just picked. So this by any node, the vertex will be the any node in this context. So we first want to check if it is visited or not. So we want to check if vertex is not in visited. If vertex is not in visited, we're gonna mark it as visited and recur on all its adjacent nodes. We want to mark it as visited, meaning that we want to add it to the visited set. So I think I'm not really sure, but I think instead we use add method. So we want to, if it is not visited, we want to add the vertex to the visited set. And then after that, repeat until all the nodes are visited or the node to be searched is found. Before that, we want to recur on all its adjacent nodes. So we want to think about its neighbors, the neighbors of vertex. So the vertex recur on all its. And after we add the vertex, the visited list, to the visited set, we want to continue to the neighbors again, just like how we did in the breadth first search. So for neighbor in graph vertex, we also want to check if the neighbor has been visited or not. So if the neighbor is not in, oh, sorry about it, I'm confused again. If for each neighbor in the graph, vertex, we want to keep going. So in the depth first search, the focus is to go as deep as possible. So we want to mark it visited, add neighbor, and then we can call the DFS, we can do recursion because we just percolate into the neighbors as we like go down the levels. DFS visited graph. And then here we want to start at the neighbor. And then I think that is it. Oh, I haven't printed it. I haven't printed. After we visit the unvisited vertex, we want to print it. That is interesting. So we have an error. If vertex is not visited, we add a vertex and then we print it. And for neighbor and graph vertex. Or dictionary. Pick any node if it is unvisited, mark it as visited and recur on the. To be searched is found. I'm gonna check. Okay. Do we need to add neighbor? Oh, because you're calling DFS on each neighbor the first. That is really true. Oh, that is true. Yeah, thank you for pointing out. We don't need to add neighbor in the for loop. So let's check the answer. So A, B, D, E, F, C. So if you start at A, B, D, and then E, C, F, E, F, oh, E, F, C, A, B, D. Oh yeah, it is right. A, B, D, E, F, C. I think it is right. And then let me go back to the questions again. Not a critical issue adding it. Yeah, you're right. And then I think the last question is, it is not clear to me that the current implementation will account for a situation where you do not choose the root of the graph as your third argument vertex. For example, if you choose C as the starting vertex, will it print out? We can try. Although I have prepared the session, I'm not like a master of all the materials. So if you do BFS from C, so I didn't know visit. Sorry. Yeah, you're right. So this only accounts for when we choose the root, because in this example we cannot go back. We cannot. So this is a one-way or directed graph. So if we start at C and then we go to F as how the breadth first search works, and then we should have like, I think we would need a method to start at to check other unvisited nodes and then percolate down from it. But this is actually how I learn in class. As far as I remember, I apologize for the unprofessional part. Depends on what objective the function does correctly search from a starting point. Yes, the same issue with the DFS. Yeah, I agree. So 12-minute warning. Yeah, we are done. So here are the resources. So in the resources, you can just like go over the articles and then solidify your understanding of graphs. And I apologize if seeing me making mistakes felt kind of like you're wasting your time or something. But I'm very I'm just an inexperienced college student, just trying to learn coding. So I hope you understand. Being a sophomore is great. Is it? I wish I was a freshman. Mistakes are normal. Yeah, thank you. Yeah. But thank you everybody for asking me questions and being here and just pointing out very thought-provoking parts. I really learned a lot just being here and just trying to read and answer the questions. So I am going to go back to the slides to end the session, but Zoom is Zoom's UX is really bad because there's a top bar when I'm sharing my screen, and it sometimes it often doesn't let me switch to another tab. So please give me a second. I really wanna go back to the slide, but I think I'll just close the collab. And hopefully, no, not the drive, not here, not the mail. Yay, I'm back. So that was it for the live coding. And our next session is about hash maps. Hash maps, and it'll be on June 24th. It is actually not June 24th, but I think I inserted a wrong image.
It's on July.
Yeah, July. This is what Rishika gave me, and I didn't check it, so that's why I have a wrong image. That was my mistake. And if you have any more questions, please ask the questions in this particular channel. And thank you so much for attending this session. I really, really appreciate everybody. Upcoming events at social media, more at Women of Code. Yeah. Thank you. Thank you so much. This never gets easy. Live coding and just explaining never gets easy. And also just trying to answer the questions often bring me the things I haven't thought of, and that's very helpful to my learning. Yeah, thank you so much for visiting this graphs workshop, and I hope you have learned something. And yeah, you are free to go.